This is Mr. Jern, and this is Gears, Pulleys, Drives, and Sprockets from Project Lead the Way, Principles of Engineering. A couple things: gears, pulleys, and sprockets. These three things are powertrain elements, and they transfer energy through rotary motion. So you have energy on one side, you get some rotary motion, and that outputs energy on the other side. It does change the speed of rotation, or it can. It changes the direction of rotation. And it changes the amount of torque, or sort of you can think of it as rotational force around an axis of rotation available to do the work. So you'll see gears, pulleys, sprockets everywhere, in different types of engines, bicycles, different types of mechanisms, just lots of places you're going to find gears and things like that. So first thing with gears, a gear train is a mechanism used for transmitting rotary motion and torque through interlocking teeth. So it's basically two or more gears makes up a gear train. And we have at least two gears. We have the driver gear, which is the one that causes the motion. And then you've got the driven gear, which is, the one that is driven by the driver gear. Thing to keep in mind is when you have two gears next to each other, when they're mated, they always turn in opposite directions, as you can see here. So if you would like them to turn in the same direction, then you have to have an idler gear in the middle between them. That way, it'll make it, you can see what happens here. When you have gears mated, they should always have, they're not going to mate unless they have the same size teeth, which are called the diametric pitch. If you've ever tried to put two gears together that don't have the same size teeth, it doesn't work. The RPMs, or revolutions per minute, of a larger gear, such as the yellow, the green one, the blue one in this case, is always going to be slower than the RPM of the smaller gear. Okay, so just look at the blue one compared to the red one. But then if you compare the green one or the yellow one to the blue one, it's greenish yellow, it's throwing me off. If you compare this yellowish one to the blue one, they are on the same shaft, and so they're going to always turn in the same direction and at the same revolutions per minute, or the same RPMs. So here's a slide. If you're, this is one that you want to go back to and refer to. This is going to be a gold star slide. There's just a lot of things to know here, because one thing that you've probably noticed about this class is the actual math itself is not difficult, but using the math can definitely be difficult. So knowing what the variables are and where they go is definitely going to be key. Now, for any quiz or test or whatever, you'll be able to use the formula sheet, and sometimes it tells you what these things are, but sometimes it doesn't. So it's just a good idea to get to know, and you're going to get to know what these things are just by practice, just by using them. So n, lowercase n, is just a number of teeth. D is the diameter. Okay, so in this blue one, you could count how many we've got. So 1, 2, 3, 4, 5, 6, and then 12 altogether is the N for this one. Okay, and the diameter is 4. W, which is actually going to be more, this kind of changed a little bit. It's going to be a little more curvy looking, will be the angular velocity, or speed. You're going to see it's a Greek letter, and like I said, I didn't notice until just this second that it's not doing that. But you could write it slightly like this, but usually when you write it, it's going to be a little bit more curvy. You'll see this example later, I'm sure. That's going to be how fast it's going around, angular velocity or speed. And this T, which again should be a little bit more, Greek looking, is going to be torque. Okay, so again, I'm pretty sure we'll see that again later. I don't know why this slide changed. So we're going to use the subscripts in and out to distinguish between the gears. So in this case, we're choosing the red gear as the input gear, or the driving gear, and the blue gear is going to be the output gear, or the driven gear. So the red one is going to be the one hooked up to the input source of energy, and the blue one is going to be the one that we want it to drive and spin. All right, so you can see we've got the number of teeth for both, we've got the diameter for both, and we've got a speed, RPMs for both, and we've got our torque for both. Okay, so in and out. And you can see your brain is kind of like putting together a pattern here, and it is just all ratios. Okay, just like mechanical advantage was all ratios, it's the same thing. So you'll see, you can probably notice the similarity between these numbers here. Okay, so let's talk about that similarity. These are going to be the equations, and these are called gear ratios. It's a similar idea to mechanical advantage. It's separate, it's different, because now we're talking about spinning things. but it's the same idea, the gear ratio. And this is essentially it. Well, this is it. So here's the gear ratio over 1, which is the gear ratio, is equal to the number of teeth out divided by the number of teeth in, which is also equal to the diameter out over the diameter in. Okay, it's also equal to the angular velocity in, so this is the backwards one, over the angular velocity out. This is the scripty, this is the more Greek looking version of it. This is what it actually looks like for the angular velocity. And then we have our torque, which is represented by the Greek tau. Also, it does look like a lowercase t, so that's why I don't know what happened in that previous slide. I apologize about that. But you can see these are all out over in, out over in, out over in, except for angular velocity. The speed is going to be in over out. Holy cow. Super easy to mix those up. So you're going to want to go carefully and go slowly and make sure you don't screw that up. So we can figure out what is the gear ratio of these two gears. Well, there's several ways we could figure this out. We could take either the number of teeth, 12 over 6. We could take the diameter, 4 over 2. We could take, and the inches cancel, the units are going to cancel out, so we're just going to get a ratio. We could take the angular velocity we were talking about, 40 over 20, or we could take the torque, the amount of rotational force, out over in. And all of those are equal to each other. And so our gear ratio, no matter how we calculate it, is going to be 2 to 1, 2 over 1. So that's just always going to be the case. That's just the nice way that gears work. All these ratios always work out like this, always. Okay, so memorize them, or at least get used to using them. Write them down. Okay, you don't actually have to memorize them, but write them down and be ready to use them. Okay, so let's see, a little example. What is the gear ratio between A and B? Okay, well, we have 20 teeth for A, we have 12 teeth for B. That's the only information we have. We don't have any other information, so we have to use the out over in for the number of teeth, 12 over 20. Okay, so the gear ratio is 0.6 between A and B. What about B and C? So we got 12 teeth, 5 teeth for C. By the way, I'm going A, B, C. We're going to assume when you go in that alphabetical order like this, that this is going to be the beginning. This is going to be the driving gear, and these are all going to be driven gears. Okay, so we're going to go in this order. This is the one pushing. The driving gear is pushing the driven gear B. B is the driving gear for C, and C is the driving gear for D. So between B and C, again, we got to use the number of teeth, 5 over 12, or 0.42 to 1. And between C and D, we have 20 over 5, which is 4 to 1. So we got our individual gear ratios, but guess what? These idler gears, what's the total gear ratio? Well, the idler gears don't affect that at all. If we were to, just like we did with mechanical advantage, combine them, we multiply the gear ratios together. So the gear ratio between A and B is 0.6 to 1, between B and C is 0.42 to 1, and the gear ratio between C and D is 4 to 1. So what's the total gear ratio? 1 to 1. What if we you could kind of, they're the same gear, 20 and 20 teeth. So that's kind of cool how that works out. What if A and D were combined together separately, or mated together individually, I should say, without the idler gears in the middle? The gear ratio would still be 20 over 20, which is 1 to 1. So gear ratios, that's just how it works. That's the math behind it. Okay. What if the last gear had 40 teeth? What if it was different? What would be the total gear ratio then? Well, a couple ways you can figure that out. Take the total gear ratio between all the gears, and so 0.6 to 1 times 0.42 to 1 times 8 to 1 now, because we would have a different gear ratio between C and D, will give us a ratio of 2 to 1. Okay. Go back, rewind this if you need to watch it again. This is kind of important. This is the math. Okay, so as you can see, the actual algebra is not difficult, and it's all just ratios. But once again, it's working with this that's going to push your brain a little bit, and it's going to be difficult to start with. Okay, the other way to figure it out is just the number of out and number of in, and 40 over 20 is going to be 2 to 1 ratio. So it kind of confirms that. Okay, what about in compound machines? Gear ratio is used very similar, as you just saw. It's similar to mechanical advantage. We use it the similar way. You talk about them separately though. You talk about gear ratio and mechanical advantage. It's not exact. They're not the same thing, because like I said, gear ratio is all about spinning. Mechanical advantage is all about linear motion, linear forces. So that's the difference. Is gear ratios are all about applying torque instead of force. that rotational force instead of linear force. Okay, that's what torque essentially is. So it's how do I say this? For mechanical advantage, the output force was equal to the mechanical advantage times the input force. Okay, we already learned that. Hopefully you practiced it and you're okay with that, or at least you follow a little bit. In this case, the output torque is going to be equal to the gear ratio times the input torque. All right, so it's the same idea, like I said, similar to mechanical advantage. So in a compound machine, when you've got more than one gear machine mechanism together, the total mechanical advantage and gear ratio are products of the components. Okay, you multiply them together. We said that already. And once again, you keep them separately. So you talk about them separately. Mechanical advantage, as we already learned, mechanical advantage 1 times mechanical advantage 2 times all the other mechanical advantages gives you the total mechanical advantage. The total gear ratio, same idea. You take the multiply all the gear ratios together to get the total. Okay, so once again, just to kind of reiterate, mechanical advantage is only about forces, linear forces, straight lines. Gear ratio is all about torques or rotational. I mean, for lack of a better word, rotational force. This is essentially what torque is. So here we have a compound machine. All right. And if you can't quite tell what it is, basically we have 3 machines in series. We have right here, this is kind of, just think of a crank. You know, you have a wheel and axle here where you would put the effort force on this end and you'd basically crank around this pink or magenta colored gear. It's just like a hand crank type thing. And then you have a gear train with the pink gear mated with the blue gear. And then you have an output crank-like thing, wheel and axle, where you have a spinning thing here, and this part rotates, we'll say rotates, revolves around that center point there. Okay, so the first mechanism is the wheel and axle. And as you can see, we have a diameter of 4 inches, 4.0 inches. We have, and the radius of this gear is 1.5 inches. And so we can figure out the mechanical advantage of dE over dr. So we have a mechanical advantage of 2.67 to 1. Then we have the gear train. Well, we have a gear ratio now, so we have to talk about it separately. And we know the number of teeth. And so we can use that to figure out our gear ratio. The number of teeth for the blue one is 24, the output, and we have the input one is 60 for the pink one. So our gear ratio is 0.4 to 1. And finally, we have our final mechanism, our third one, another wheel and axle. So this thing will just spin around this pivot point right here. We have another 4 inches for the crank, but the radius of the input is only 0.6 inches. So dE over dr. The effort force is going to be this blue gear, which is trying to turn this crank. And so that's the effort force. And the resistance force is going to be this crank right here, this part of the lever, or I guess you could call it lever, this external part right here that's trying to turn. So the total, again, mechanical energy is just you take the mechanical advantage, I should say, is going to be the mechanical advantage of the first wheel and axle times the mechanical advantage of the third machine, which is another wheel and axle. And so you multiply them together. And so the total is going to be a mechanical advantage of 0.4 to 1. Separately, the gear ratio total, there's only one set of gears, one gear train. And so that's the second machine. And so the gear ratio is going to be 0.4. So you talk about them separately. That's how you do it. What about when you have a compound gear train? Well, let's check it out. We have our green driving gear here, spinning pretty fast because it's kind of slow. And that is driving a yellow gear here, and that's moving a little bit slower because it is bigger than the green one. But then on the same axle or axis, you have the blue one, which, as you can see, is spinning at the same RPMs as the yellow one. And then being driven by that blue one is this giant red gear, okay, moving much, much slower because it's much, much larger. So the two middle gears, like I said, have a same axis, so they move at the same speed. This basically what you're doing here is because the blue one is able to move a little bit faster, it makes this thing move a little bit differently, and so it allows the final gear to rotate slower, and it produces more torque than if it were connected to only the driving gear. So it's kind of nice how that works out. Okay, so what about what do you mean how does that work out, Mr. Jared? Well, if you take a look at the math, that'll kind of go through it a little bit. So look at the gear ratio between gear A and B. Okay, the green one and the yellow one. Well, the number of teeth for the green one is 10, and the number of teeth for the yellow one is 40. So we take that 40, divide it by the 10, and we get a gear ratio of 4:1. Between C and D, you have 50 and 20 in this case. So 50 divided by 20 is going to be 2.5:1. And so the green and the yellow sort of acts like a separate gear ratio compared to the red and the blue, but they're working together, so we multiply them together, and so we get a total gear ratio of 10:1. Okay, that's much better than if we were to do just the straight red to the green, which would give us a gear ratio of about 5:1. Okay, so this really kind of changes things a lot now when you combine them like that. So it's always an option. So that's gears. Belts and pulleys are similar-ish in that we have a lot of similarities, but we don't have the teeth necessarily. They're not meshed together. We have a belt and pulley is sort of like you kind of know what this looks like. It looks exactly like it is, basically. And the equations we're going to be dealing with is more focused on the diameters than any kind of teeth, because we just don't have teeth. It's literally a belt. Like think about the timing belt in a car or something. So the diameter out over, it's the same equations. We're just we're gonna use them in the same way. Okay, there's not much difference here, is my point. Okay, it's just we're talking about slightly different mechanism. So once again, though, the D is a diameter. This Greek letter that looks like a W is angular velocity, and then we have this Greek letter that looks like a lowercase t is going to be our torque, and we get all this information from our little diagram up here. Okay, so what is the gear ratio here? Well, 6 inches over 2 inches, or 30 over 10 RPMs, or 55 over 18.5 foot-pounds of torque. All those work out to be basically the same thing. So is the gear ratio of 3:1. Okay. And finally, sprockets and chain system. This is something you see on a bicycle, obviously, and a lot of other places. Once again, it's the same equations. There's not much to it, really. Once you get the gears and everything else, you're going to be fine with this. So it's the same equations, diameter, RPMs, all that stuff. Just kind of, just be able to identify the 3 different things, and you're going to be fine. So in this case, it's the same idea before. I'm not going to belabor this math. In this case, we have a gear ratio of 2:1, and no matter how you count it, no matter how you calculate it, it's going to be the same, okay? Because all these equations are the same. You just got to get used to using them is all, and identifying what's what, input, output, that kind of stuff. And you make sure you don't mix up the rotational velocity one, because that's going to be the one that's different, okay? So a little quick comparison before we wrap up. A pulley is going to use a belt. This is obviously not gears. Gears we talked about in depth. That's like they're meshed together and mated together. So a pulley and belt system is going to use a belt system. It's going to that's how it's going to transfer the force. A sprocket and chain will obviously use a chain system to transfer the force. What's the difference? Why use different ones? Well, a pulley system, the advantages is it's much more quiet. No lubrication needed. I mean, if you're taking care of a bicycle or a motorcycle or anything that uses a chain, you do have to oil that sometimes, lubricate it. It's also inexpensive. Typically the materials is not metal, and it's a little bit cheaper. But the disadvantages is it can slip. Although sometimes that is an advantage if that's what you want to happen. But yeah, so for a belt and pulley system, these are the advantages and disadvantages. For a sprocket and chain system, well, you get no slip. I mean, once that chain is engaged with the sprocket, think about a bicycle. There's no slipping. It's not going to happen. Okay, it will literally tear through your shoelace or whatever without slipping. It's much greater strength because it's got that teeth to kind of just pull on the chain, but it's usually more expensive. It needs lubrication. It's a little bit more noisy. So that's it for this. So again, any questions, please send them my way. All right. See you later.